It's important to note, for posterity's sake, I'm putting this online. I did not have to be reminded. I did this entirely on my own. Okay? I want my attaboy. Moving on. So, it's that time again, boys and girls. I mean, come on. I feel like the enthusiasm is waning. Things I would know if I were you. Number one, I'd probably know torque. That seems important. Number two, I would probably know sum of torques. Now I will put this over on the side, but I'm going to put this as equations, okay? Both in the form of equilibrium, aka sum of torques is equal to 0, and sum of forces is equal to 0. Plus, I would know it in dynamics. Dynamics means what if it's not equal to 0, aka what if sum of torques is equal to I alpha. I don't know what my parentheses are doing there. Let's just get rid of them. They're not being helpful. Organization tools are only helpful if they're helpful. All right, number 3, angular momentum. I'm just going to keep going with symbols now. There we go. I would know that one. Nah, I should write it out. Don't be lazy, dummy. Angular momentum. And I would argue that should say rotational kinetic energy. Because rotational energy makes it seem like there's a new thing called rotational energy, and there's not. It's all energy. Since it's going to bug me, I'm going to fix it on the spot. Well, you guys write down the last few. There we go. Oh, it doesn't change second hours. Hold on. Quick aside. I've got to do it. All right. While I'm doing arguably an OCD thing, what can I do for you? What do you need? We have questions on. I feel like the people on the video are going to be very disappointed if you ask 0 questions. Also, there's a bear on a unicycle. Just thought you should know.
Can you go over a problem with rotational and kinetic energy?
Probably, yeah. What do you want me to do? Ball going up a hill or down a hill? Those are your main ones. Let me show you this because I think this is kind of interesting. Okay. I'll go a ball going up a hill, but 6 of 1. Okay. Here's an interesting thing. If a person were to play, say, skee ball here, okay, and they got the ball, rapidly propelling the ball. Here it is. These are 2 different moments in time. They're not just rapidly throwing a bunch of balls here. Okay. What type of energy does the ball have right now? Be specific. There's more than one. Try again.
Is it in the air?
What's that?
Is it in the air?
Yeah, it's in the air. So right here, before it's hit the ramp. It would have translational, but it would not necessarily have rotational yet, right? I guess it's kind of hard to see without knowing the situation. So don't beat yourself up if that's what you're thinking. But like, more than likely, you throw it. It just has kinetic, right? And then it would have rotational once it hit the ramp. But let's say I asked you, like, how high does the ball go? Does the fact that it was rotating in the middle actually matter whatsoever? No, it doesn't. Because it starts entirely with kinetic translational, okay? And then it ends entirely with gravitational. The fact that in the middle of it, the fact that it had kinetic rotational, who cares? Okay. Now, if a problem instead said, as I believe many of your problems actually do, that the ball starts on the bottom of the ramp and gives you a speed, now we've got a little bit more of an interesting situation because, yes, now it would more than likely be rotating as it's spinning. So here we go. We have conservation of mechanical energy, which you should always write down the original equation, especially if those of you that potentially struggle with these type of things, You're getting points for putting down the correct equation that you're supposed to be using, even if you do not manipulate it correctly. Next, do not skip steps on this. Write every type of kinetic energy every type of energy that's going to change in the situation. What types of energies are going to change in this situation as the ball goes up the ramp? We're going to try to figure out how high the ball goes because of how fast it started. Like, I'll give you the ball will start with the speed of 2 meters a second. Okay, and the question is, how high does the ball go? Cool. All right. What do you got?
Kinetic transition.
Agreed. So I'm going to write kinetic translational initial and kinetic translational final. Next. Gravitational initial and final. And in this case, since the ball starts at the bottom, in this particular case, then yes, it would already be rotating, so it would have rotational. Okay. Do we have any elastic here? Nope. All right. After you've set all of these up, I would immediately start canceling. Okay. It is a good thing to put all of these up here because sometimes, like I commented a second ago, with the ball being in the air, if we don't look very closely, we might just kind of get into this kind of like pattern as opposed to like looking at what's going on. So, which of these should be 0 and why? Gravitational which one? Talk to that a little bit. Okay, I agree that that's what mathematically I would do it. What are you technically saying? Are you saying it has absolutely no gravitational energy? What are you saying then by making that 0?
You're saying that you place the height of 0 at where it starts.
Correct. And more importantly, it means this height that we are measuring is technically from that particular spot. But yeah, 100%. Cool. Okay, what else? Yeah, at the very end, kinetic translational should not be should be 0 because I'm moving, and rotational should be 0 because rotating. Okay, from here, I will tell you this work, as always, given and define the equation. That's usually, those 3 pieces are where the physics is actually done. It's the very math beyond this point. So please keep in mind, especially if you run out of time and stuff like this, I front load, definitely front load points as far as this stuff is concerned. Simply right here, you are looking at a bulk of points. Now we fill out individual equations. That guy is 1/2 mvi squared plus 1/2 so squared. Okay. Oh, Tina, do you have a loaner? All right, so is equal to mgh final. Now you'll note that I did not give you mass. Okay, it'll give you mass. More than likely, somewhere in the situation is going to cancel, but please make sure it cancels at the right spot. It should not cancel yet. Why does it not cancel yet? Well, you're getting technical with it. I was actually looking for just, there's not a mass in every equation, but yes, you can see where it's going to go. All right, so from here, because I have VI, obviously, VI, I want to leave that VI around, but the one that's kind of confusing, of course, is the fact these 2 guys right over here. So we're going to expand both of them out. I said skee ball, so that would probably be what kind of shape? I would agree with you. I don't have that fraction off the top of my head. Do you guys yet?
2 fifths.
2 fifths? Is it 2 thirds?
2 thirds is the empty one.
You sure?
Yeah.
Okay. Here's an easy way to actually check that real quick. 2 fifths. 2 fifths is the smaller one, 40%, and you know that solid should be smaller because it has more mass closer to the center. Yeah. All right. So 2 fifths. Mass, radius squared. Okay. And right here, Obviously, we don't know angular velocity either. How do I get rid of that? Yeah, that equation from last chapter, which we wish would go away, but sadly does not. Okay, and that makes that velocity initial over r, but notice the squared on that means both should be, everything inside should be squared. If you find yourself consistently forgetting to do that, I would probably suggest that what you do instead is take a little bit of an extra step and just say, hey, omega is this, and then put that squared right up there just to remind yourself that, hey, everything inside should be squared, not just the VI as some people do and then make a mistake because of that. But there we go. And finishing this math off, it gets relatively downhill from here. I wasn't going to say easy. I was going to say easy, but I shouldn't have. All right, oops, let's go. All right, what's cancels what? Radius squared gets canceled, right over here. So we don't need to know what the radius actually is. What else? Mass is in every term, so mass is going to cancel right here. And you're left with, this is 1/2 VI squared plus, let's go cancel right here, that is 1/5 VI squared equals GHF. It's a terrible 5, let's do better. Okay, common denominator, what should I probably use? 10, so 5/10, 2/10, I get 7/10. And to find HF, all I'm going to be doing is dividing by G. So I don't have to move this at all. 7/10 VI squared all over G is equal to HF. So that should be what? 4, 7/10 of that would be 1.4 divided by 10 should be 14 centimeters roughly. Or a little bit more because it's 9.8, but I got 14 centimeters. 0.14 meters. Right? No, I screwed up. That's twice that. I screwed up. Because that's 4.7, 1.4, 2.8. Yeah. Roughly 2.8. A little bit more than 2.8 though, so let's say 0.3-ish. What is it actually? 2.9. 0.29. There you go. Sorry. There you go. How was that? Helpful? Your main moves in this particular one are, like I said, set up that it's conservation mechanical energy, do everything that changes, cancel what cancels, and then again, in the middle, the tricky part is filling out that moment of inertia and filling out that angular velocity. Several of you saw in the lab that there was a problem that actually has to go the opposite way. Like we found, when we did a problem in class, we found velocity initial, which of course is the exact same thing, except right here you do algebra a little bit differently. If I'd given you height and come back down the opposite way, like literally if the ball then stops up there and starts rolling down the opposite way, it's the exact opposite. Okay, so if the problem asks you to find VI, do the algebra. What if it had asked me to find angular velocity? Well, you have two things you can do. Okay, my personal preference, because I think it is a little bit cleaner, is instead of substituting right here for VI over R, okay, from omega, what I would personally do is substitute for V, which of course V is omega times R right there. Okay, in which case obviously you would need to know R. R would no longer cancel. I would have to tell you what that is in order to calculate that out and then solve for omega. But let's say you don't like that. Let's say that's not quite as clean. Your other option, of course, is if you had found VI, well, then you just have, just like we said earlier, angular velocity. You can do that at the very end, and that will work as well. Questions, concerns? Humor me. Give me a 0 to 5 on energy problems in rotation. Where are you guys at? Okay, cool. All right. What else we got?
So on the Atwood machines problems,
Sure.
Whenever we have the 3 equations, 3 unknowns,
Sure.
whenever you're going with the the torques of the pulley, how do the lever arms cancel out?
Lever arms cancel out? Oh, I know what you're talking about. Yeah. Okay. So do you mean do you want me to just do essentially the lab one? Okay. So doing the force diagram, right? I'll do the lab one first, okay? The big mistake that people make, I want to make sure I'm as consistent to most people as possible. How did you guys number, label these, whatever? Probably similarly to what I did, but what did you do?
Class 1,
1 and 2.
and then I did 2.
Cool. And which one did you guys say was bigger? 2 or 1? 2, probably. Okay. All right. So let's call this guy, obviously, let's call the easy ones, force gravity 1, and because you said it was bigger, I'm going to go quite a bit bigger here, force gravity 2. All right. Now, tensions, okay? Which way is 1 going to go? Up. It's going to accelerate up, so tension on it should be bigger, equal, less. Bigger. Please be careful with these force diagrams. Probably the biggest thing that I'm going to grade on this is the force diagrams, okay? More so than probably even anything else. All right, so tension 1 should be bigger, and that's equal to tension 1 over here. As a matter of fact, I screwed up on this picture because this should be unbalanced up here. And torque 2 over on the second one over there, should it be bigger, smaller, equal? Smaller. Yeah. How come? Weirdly, it should, and if I did this correctly, which I think I actually did in this case, it should be smaller than this. It should be, sorry, let me, for the people online, this should be smaller than this, but this, which is the same as that, should be bigger than that right there. Right? Okay, so the question on the table is, why does the radius on the upper cylinder cancel? So let's sum of torques. Actually, before we do that, that way's positive. Okay, sum of torques, which would be the torque of 2, which is now positive only because I established this way. Usually it would be negative due to going clockwise. Okay, minus torque 2 is equal to I alpha, which I, since it's a cylinder, is 1/2 mass of cylinder radius squared. And, well, I'll come back to that in a second. Okay, now, I'm pretty sure you're good on the bottom ones, but I'm just going to check to make sure. Sum of forces on 1 is M1A. Sum of forces on 1 over here should be positive T1 minus M1G equals M1A. Any questions about that at all? Cool. And then sum of forces on M2. Only major difference, of course, is the switching of signs because of that guy right there. So now, force of gravity of 2 should be positive because it's that direction, minus T2 equals M2A. Now, in this particular setup, I believe you were asked to find moment of inertia. Which one was it? Yeah, you were asked to find moment of inertia. Radius shouldn't cancel then, if you're trying to find moment of inertia.
Okay, I just did it through like finding the acceleration.
Sure, which is fine. 100% fine. But even if that's the case, you're still going to need to know radius to eventually get moment of inertia here. Okay, now with finding acceleration, I can show you that it does cancel in that particular case, but it will not cancel to find the answer that we're looking for. So right here, let's say we're trying to solve this problem for acceleration, the way that was just said. Okay, as a matter of fact, my setup, I'll just tell you this real quick. I looked at it and I laughed because the way you do this, you don't, if you find it, you guys already found acceleration, if I'm not mistaken here. It's not a 3-equation, 3 unknown. It's 100% not. You actually can solve everything individually without using multiple equations, because once you know acceleration, you can solve T1. Once you know acceleration, you can solve T2. You can plug T1 and T2 up into the torques and you're all set. But let's say, for the sake of argument, this was a different problem and we were trying to find acceleration instead. Well, if we're trying to find acceleration, getting ahead of myself, my apologies. Let me do one other thing first. I'll promise to come back to that sentence. These two torques should have their own, and always stop me, I screwed up this one. My apologies. These two torques should get their individual, which should be the radius times tension 2, and those are perpendicular, minus the radius times tension 1, Why did I not put radius 2 and radius 1 on these? The same amount, correct? And that's equal to 1/2 mc r squared times alpha. Now immediately right there, you'll notice that one of the r's cancel. Sorry, both r's on the left side cancel. One of the r's over here cancel. Okay, we are not yet to the point where all radius entirely cancels because of the one over there in that right term. But when you try to switch out, do the substitution for angular acceleration, that's going to be that angular acceleration is equal to a over r. And this r cancels with the second one of those right there. So that way you're left with t2 minus t1 equals 1/2 mca. Does that make sense?
Yeah, I just didn't like think about, because I just kind of like went with this because I wasn't sure on where to put the lever arm as, and I didn't think of it as being like the fulcrum force.
Yeah, you always, I'll tell you that right now, if you're ever struggling with lever arm, I mean, there's a reason why I've been redundantly, to a certain degree, even saying, like, know the definitions, because anytime you get stuck on any one of these problems about fulcrum, about lever arm, about anything, you just go, fulcrum is the point of rotation, it can't angularly accelerate, I get to choose where it is, which means the only spot you can choose in this thing is the middle of the center. Lever arm, by definition, is the distance from where the fulcrum is, which has already been placed at the center, to where the force is applied, which is on the outside, which automatically makes it radius. There you go. Okay, other questions?
Could you get a guiding help with force problem part B?
Absolutely, yeah. Oh, the force problem. We talked about this one. Not to say that that makes it easier by any stretch of the imagination. Because it's hard to get. A lot of these concepts are very challenging to get within a limited period of time. Alright. What's up? I gotta explain stuff. Hey, it's already pulled up. Somebody already knew. So, darn it. Come on. Computer, don't be slower than me. There you go. Probably shouldn't speak condescendingly to the computer. There we go. All right. So for starters, I think one thing that makes this complicated is the fact that you're looking at a rear end the whole time. It's just very distracting. No, the fact that you are looking at something that is kind of like all over the place. So one thing that can be very helpful in your particular setup is just treat an object like it is just a straight line. So like, essentially a ladder. Okay? So here's my force diagram. Here's kind of like how I would do it probably a bit on my page. Here's force of wall. Here's force of gravity. What other forces would go in this setup? Force normal, correct. Go straight up. And we can see from the sum of forces that we are missing a force. Yes. What did I mean by that? To say that I could see from sum of forces that we're missing a force? Yeah, there's a force to the right, which means that if we don't balance that out, the horse is going to go right. And so there has to be something keeping it going right, which would be right down here. That would be force friction. Now, this problem is actually, I think, simpler than a lot of students make it out to be, which I don't blame you because I think the picture doesn't help on that particular front. But let's say my picture on the right over here is how the setup goes. Where would you put your fulcrum? Definitely you put it on the feet, right? Because that eliminates the torque of two different systems right there. And now the torque of the other two are completely equal to one another. Now, usually what we would do in this case is we would sum the torques equal to 0, which is what we should do. We should see that torque of wall should be negative because it's clockwise, torque of gravity positive, blah, blah, blah. Great Spanauer, we get that gravity and wall are equal. Everybody cool to that point? Again, this is one of those spots where I would say, like, if you want to, like, understand it, the bulk, that's the biggest thing I need you to see right there. Now, the trick to this problem is that usually you would say this, r times force times sine theta. Okay, well, let me draw both force and theta and tell you why that's dumb. Okay, so here's the lever arm for force of gravity. From the force to the fulcrum, right there. And the angle is from the lever arm to the force, right there. That's not particularly helpful of color. Let's go a little bit more here. Let's try that again. Okay, well, here's the lever arm, and here's the angle. I don't know the lever arm. Admittedly, in this one, you could actually find it. Just, 1.4 squared plus 0.35 squared is the whole thing. The angle, of course, you could also find using trig. But here's the deal. What is the point of sine theta? The point of sine theta is to make sure that these two are perpendicular to one another, right? Well, watch this. If I just get rid of sine theta and put that little guy right there, then what this says is I need to either know how much force is perpendicular to r or how much lever arm is perpendicular to force. Meaning, instead of this picture right here, what I really need is and also I kind of drew it in a weird spot. That should be the lever arm, that should be the angle. What I really need is I need to know on this triangle for lever arm, here's r that's parallel to the force, here's r that's perpendicular to the force. Do I know how much r is perpendicular to the force? Yep. So this is 0.35 meters. And this, if I'm not mistaken, wasn't the horse 500 newtons? 500 kilograms, okay. So times, a little bit different, 500 kilograms times g. Right? Okay, so that would be the gravity over here, and that's equal, I don't know, I'm switching colors here, that's confusing. And that's equal to, once again, lever arm of the wall times force of wall times sine theta of wall. But it's the same conversation we just had. Let's go ahead and get rid of this real quick so we can see this picture. Here is the lever arm for the wall. There's r, right? And the angle for the wall is right here, from the lever arm to the force. And that's annoying to use. But once again, we reiterate the same thing again. But if I just get rid of sine, and I remind myself I need these two to be perpendicular to one another, and I redraw this triangle, okay, this would be r. This is how much r is parallel, because this force is to the right, and this is how much r is perpendicular. Do you already know how much r is perpendicular? Yep. So this ends up just being 1.2 meters times force of wall. And the rest of the math is pretty easy to do, yes? Yeah. The concepts there are kind of hard. Like I said, the math is pretty easy. With the rest of the problem, that would get you, that would give you force of wall. Okay. In turn, if you go back to my picture over here, if you have force of wall, what do you also have? Force friction. Okay. You already, I believe, from part A have force normal, right? No, I'm sorry. You already calculated force wall from part A. My apologies. Okay. So never mind. So you have that. You had this already. I am so sorry. I didn't look at. I assumed that was the problem. Apparently, it's not the problem. I am so sorry. So these two are equal, and you know these two are equal, right? So if it wants the total number, the force on the feet, you would just make a triangle out of it. There's the total force on the feet. Just a combination of force normal and force friction. Careful with that because I believe it gives you the angle with the vertical, which is this one up here. Okay. So when you do inverse tangent, if you want that angle, your opposite, of course, is going to be your x, and your adjacent is going to be your y. And then finally, minimum coefficient of friction is going to be super easy because you have force friction and you have force normal, so just divide the two, and you're all set. Well, my apologies for explaining something that you potentially didn't need, but I'm going to go ahead and go on a limb and say that probably someone in the room did need it, so I'm justifying my actions post. That's not the way you want to do it, but I am American, so that's how it's natural to my state of being. What's up? What do you need next?
Can we go over number 8?
Sure, absolutely. I got this one memorized because of a lot of people that have asked me. Very similar, obviously, to the Atwood machine. Let's go. I'm gonna blow the picture up of this guy right here. Force gravity 2, tension 2 should be less. There's tension 1, there's force normal, there's force gravity 1. There's tension 1, tension 2, oops, yeah, that's fine. Force gravity, and technically, since it should be there, force normal. Questions on any force diagrams to begin with? Okay, I believe it said no friction in the situation, yes? Again, people's big issue is that tension 1 and tension 2 are different, and how do I know tension 1 and tension 2 are different? Well, if tension 1 and tension 2 were not different, would the object, would the pulley rotate at all? No, torques would be balanced and they would not rotate. So this is possible to have different lengths of string actually having different amounts of tension, but that kind of makes sense because imagine that like one of your friends is pulling on your left arm and somebody else is pulling on your right arm. Can one of your arms be pulled tighter than the other one? Yeah, it is possible to have one not being pulled as much. As a matter of fact, if you were doing this and one was being pulled more than the other, this is the exact reason why you would accelerate in that particular direction if they were pulling hard. Okay, from here, I'm going to set a direction. Here's the direction. That way is positive. The general way I set the direction is just the way it's going is positive, because otherwise we would have said that was positive, that was negative, and that was negative. Okay, so now we're saying everything is positive. Hopefully you see that you need to shift the axis on the bottom one. Okay, and then if you do the trig, there's the angle. So we need that amount right there. So summing the forces on mass 1, we would get positive tension 1 minus force gravity in the x. Now, if you can do this trig quickly in your head and you know you're not going to make mistakes, feel free to make this skip like I'm about to. But if not, I would 100% go over there and make sure your trig is good. This should be m1g times the sine of the angle. And it's kind of hard to see in my triangle here, so I'll show it again. That's because the angle is here, that angle is there. This goes all the way back to like chapter 4 where we did this, and we want this one over here, so it's the opposite. That's why we're using sine. And then we sum the forces on the hanging one. That should be pretty easy to do. That should be m2g, force of gravity, minus t2 equals m2a. And then the torques up here. Sum of torques is equal to I alpha. That should be torque 2 minus torque 1 equals, well, we'll just leave it as I alpha for right now. And now we'll do all our substitutions. This should be the radius is the lever arm, because our fulcrum is going to be in the middle, times tension 2, and those are perpendicular, minus the radius again, because that's the lever arm, times tension 1, and those are perpendicular, which is a little bit weird since it's down there, but if you look at the picture carefully enough, you should see that, yep, both of those are 90 degrees, is equal to 1/2 mass cylinder times radius squared times, I believe we're trying to find acceleration, correct me if I'm wrong. So I'm just going to go ahead and do that substitution real quick. And at this point in time, wait, no. You were given moment of inertia, weren't you? My apologies. I apologize. I'm trying to remember the problem off the top of my head, and I'm making mistakes. So since I'm given moment of inertia, I will not do the substitution I said just a second ago. But I will still do this one right here. Now be careful with that equation now. Does radius cancel? It doesn't. The trick to that is that people look at that and go, but Spainhour, there's a radius in every single term. Yes, there is, but when you got to think about canceling, if you're not sure, just do the work quickly in your head. divide everything by the same amount. Divide by r, that cancels. Divide by r, that cancels, which is great, except divide by r, that does not cancel. Actually, but I'm going to still do it because it simplifies things a little bit. Squared. Now I've got my three equations with my three unknowns, being tension 1 and acceleration, tension 2 and acceleration, tension 1, tension 2, and acceleration. Now I've mentioned before that my personal preference on this is elimination. If you still prefer substitution out of simplicity, I would highly, highly suggest you get good at elimination, which takes some practice because it'll be much quicker and much cleaner. But if you have to do substitution out of what you're comfortable with, that's fine. You'll notice that if I add everything on the left side of the equal sign, my T1 here and here will cancel. My T2s here and here will cancel. So I'm actually just left with this M2G minus M1G sine theta. And I think that's it because we've canceled that. We have that one. We've canceled that. We have that one. We've canceled both of those. And we need to set all the right sides. So that's M1A plus M2A plus I, let's go I over R squared. And my apologies for using the digital media here to factor out my A, which you can't do nicely on the paper, but I factor it out. And I divide underneath and I get M2G minus M1G sine theta divided by M1 plus M2 plus I over R squared. Boom shakalaka. Questions on that? Where were you getting stuck, if I might ask?
I don't even know.
Okay. It's not the easiest of problems to see. So.
Can you go over like a little bit of station 2 for the lab? Because
Sure, I can. As the rotation of the angular momentum. Yeah. But you do have a couple of apologies for people online. We do have a couple of angular momentums problems on the board that I'm happy to go over as well because they're kind of already nicely set up. The one on the left, we've kind of gone over both of these in class, so if you don't, I completely understand. But the merry-go-round one's on the left, and the ball running into the door one is on the right there. But so the main thing to understand is that you're rotating the tire at the very beginning, but you're not rotating it on the axis that we're spinning. So technically that means its angular momentum on that axis is 0. Does that make sense? So here it is in a nutshell. You have all the angular momentums at the beginning equal to all the angular momentums at the end. So we have angular momentum of the wheel initial plus angular momentum of the person initial. Ooh, I don't know what that W was. Angular momentum of the wheel final plus angular momentum of the person final. Now, which of these cancel? Yep, that's going to cancel because? Correct, you're not rotating at the beginning. But actually, also because of what I said a second ago, wheel should also be 0. So what's my total initial angular momentum? 0. So simply put, this means that if I do some real basic math here, this means that the angular momentum of the person final should just be equal and opposite to the wheel final. Which says what? Well, it says that if the person's spinning clockwise, what do we see the wheel doing? Spinning counterclockwise, which is exactly what happens. And who's spinning faster, the wheel or the person? Probably the wheel. Why? Well, if we expand this out, no, we should probably put this differently. Actually, this is omega final of person, and this is omega final of wheel. Why should the wheel be spinning faster? Why should the wheel have a larger angular velocity? Because it is a smaller moment of inertia. For calculating moment of inertia, just a quick heads up. I told you to treat the person as a cylinder, which is a little bit weird because you're not obviously a full cylinder. Do make sure that the radius that you're using in that case is not out here, definitely, because that would imply that all of your mass is like this. So, and look at all this empty space that we're not filling up. So if you're going to use cylinder, which you should, you're going probably, and this is still a little bit off. You're going to shoulder. But you are still assuming that you're a cylinder, which I don't think anybody in here actually is. So keep that in mind, but we're using 1/2 mv mass of person times radius of person squared, but radius of person is, like I said, for the shoulder. And moment of inertia of wheel. It is rotating around itself, but it's still mr squared. Why?
I think this is where I got stuck in the math part of it. The mass is centered on the outside.
Yeah, these equations are meant to basically always use mr squared. Okay. The gist of that is if I spin this tennis ball right here, is all of the mass at the radius? No, there is some mass, like you can see it, like that's closer and closer and closer and closer. So technically, the way to actually get moment of inertia of a complex object like this is to take small pieces, like the mass of this piece out here, do its mr squared, then this mr squared, then this one. Now that's very, very complicated to do and very time consuming, which is why blah, 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 enter calculus later on for those of you continuing down that path. But simply put, that's how you technically do it. Now I've given you fractions for when an object spins around itself, but a wheel is pretty much all of its mass is roughly at that radius, which is why it should still be mr squared. I like that we've covered angular momentum, we've covered energy, we've covered dynamics, we've actually covered a bridge problem, so this is going, I'm a big fan. Any other questions?
Can you go on 8.7 number 3?
Sure.
I started doing some funky stuff on there.
Sure, it happens. If you have not, I would say, if you've been taking physics, this much physics, and have not restarted the same problem at least 3 times at some point in your, I mean, I feel like you're not doing it. Like, I had a buddy of mine in college that was very much like, he's like, I tried it once. And I was like, well, that's your problem. What? Is it, you only tried once and you didn't get it? It's not that hard. You're not dumb. You just keep trying. It's all it is. All right. Sure. Okay. So this is technically not the same conservation of mechanical energy. It's just using a lot of other stuff that you know. A horizontal 800 Newton merry-go-round with a radius of 1.5 meters is started from rest. The moment you hear start from rest, what should probably be jumping into your brain?
Velocity initial.
Yeah, angular velocity initial. Angular kinematics should probably immediately jump into your brain there. Through a constant force of 50 newtons applied tangentially to the merry-go-round, find the kinetic energy of the merry-go-round after 3 seconds. Again, it said after 3 seconds, so. Here it is in a nutshell real fast. I almost don't want to do this one for you because I feel like you can do it, but I'm fine with it. So here's the merry-go-round. I'm drawing it from a weird perspective right now because there's its force of gravity, and the force, the 50 newtons is out here, or in this case, 50 newtons is out here. Now I do that specifically to point out a couple things. One, is force of gravity going to cause torque? No. So why were you probably given force of gravity? To go get mass. Yeah, because mass is equal to force of gravity divided by g, correct? Now, what do I do with a torque? Well, we're told the radius, we're told the force, so we can get torque. And there's only one torque on it, right? So you could easily get the sum of torques. Could you easily also calculate moment of inertia? Yep, that'd be 1/2 times this mass times the radius we just mentioned squared. And then that radius, which I think was 1.5 meters squared. Okay. And then what could you get out of that? Angular acceleration. Do you already have 2 angular kinematic variables? With a 3rd angular kinematic variable, what could you then calculate? And then you just plug and chug into that equation.
Okay.
I would give you that. Omega final will give you that. And you're all set.
Yeah, I didn't use angular kinematics. I used sum of forces, and I like.
Sum of forces is not going to be helpful. Because technically, according to sum of forces, I didn't finish this force diagram. This should have a force normal up, and actually, because of this force here, there should be a little bit of force normal like out of the board here. In other words, force normal should actually like come out and go that way a little bit to counterbalance that. But that being said, don't think the merry-go-round's accelerating anywhere, so sum of forces is going to be equal to 0. Other questions or concerns? Give me a 0 to 5 how you feel about the test. I don't know if 3 half fingers is the same thing as 3 fingers. Okay, I think 3 half fingers is close to a leg. Like when your hand looks like it's like dealing with rigor mortis over there. Like I want to show him a 3, but I don't want to be held responsible for this 3. I think it's like 3 half fingers. I tricked him. It's actually a 1.5. Gotcha, Spainhour. Looked like a 3. Any other quick questions before we? All right. Everybody online. Hope you have fun. That's an ominous way to put that.